Hey there, physics students. Welcome back to another edition of Rapid Review Series for Honors Physics. Today our topic's going to be area under the curve. What the heck do I mean by area under the curve? Let's talk about it. Okay, so let's start with an example, right? So here's some graph. You might have seen one like this in a homework assignment. It's a velocity time graph. I'm going to exaggerate the axes here so you can see what it is. I'm going to include units, as I always like to do, meters per second and seconds. It's a velocity time graph. And the question is, how far did this object travel between time 2 and time 5? Now we know that the velocity is 0.5 at that level. I know it's probably hard to read in the video, these numbers. Here's 2, here's 5, right? So you're going at 0.5 meters per second of speed and in the positive direction, because this is the velocity. And you're doing it over the course of 3 seconds from time 2 to time 5. It's kind of easy to visualize, right? So let's see, going 0.5 meters per second, and a second goes by, that means I've gone 0.5 meters. Another second goes by, I'm doing mental math, 0.5, 1 meter, right? And 3 seconds, you've done 1.5 meters, right? Kind of obvious almost, right? So if you look back at the graph, what you've really done is you've taken 3 seconds, right? And you've multiplied times 0.5, right? That distance is 0.5. And if you look at that, that is something you've done in geometry class. You've just taken an area of a rectangle, right? The base times the height. That's the rectangle. So turns out that if you take the area under the graph for this rectangular curve, you can find out, this rectangular graph, you can find out that the area is the same thing as the displacement. Let's go check the other end over here. If we look at the area later, it looks like the same area, but we know that the velocity is negative here, right? It's a negative velocity of negative 0.5. And so the displacement must have been negative. Looks like for this whole trip, since those areas are the same, it looks like that object is back where it started from. Okay, so I can conclude, if you look here now at the conclusions, I can conclude that for a rectangular velocity time graph, the area under is displacement. And as long as I remember these two kind of things where the area can be positive or negative, unlike geometry class, right? So by definition, if it's above the line, if it's above the 0 line, it's positive displacement. And if it's below the line, it's negative displacement. Okay, so these are plus displacements and these are minus displacements. Little comment is, if I say curve, I mean a graph, right? So it doesn't have to be curvy. It doesn't have to be a curvy curve. It can be kind of rectangular looking, like in these examples here. You know, here's the one we just looked at, but this is totally legit. Even this crazy thing is totally legit. And this one that looks like it's piecewise linear, that's fine. Those are all, I'm going to call them curves in general. And I'm going to make a claim now that not only for a rectangular curve, but for any velocity time graph, the area under the curve represents the displacement. This is a really strong statement that I'm making, right? I said, for a rectangular, yeah, that sort of made sense, right? For a rectangular, it made sense to you, right? It was kind of intuitive. Now I'm making a much bigger claim. For any velocity time graph, the area under the curve represents the displacement. Big statement. I'm going to make that only a claim right now, and I hope I can convince you that that's true a little bit later. Okay, so let's try one here. This is a little more interesting than the rectangular one we looked at. I'm going to focus on segment A here, and I'm going to look at the area under the curve. And for segment A, I can determine that the displacement, which is the area, is 3, which is the height, times 30, that's 90. But I have to divide by 2 because it's a triangle. So the displacement, I'm going to write delta x, is equal to 3 times 30 divided by 2, 45. Okay, so that's 45 meters. Done. So I just looked at the area of that geometric shape. It's easy when it's plus. Let's go do a -1. I'm going to go down and do segment D. Let me do segment E instead, all right? 1/2 the base times the height. So 1/2 the base, which is 10, 10 units, times the height, which is 2, that's 10, right? So the answer is 10 meters, and I have to remember to put the negative sign there because it's a negative displacement, right? Negative velocities lead to negative displacements. A few final comments about these graphs and how to look at them. In a lot of these exercises, we look at them segment by segment. So I said for segment A, how far did the object travel? I mean for the segment A. Don't worry about the transitions and the sharp corners between the different segments. They're a little bit unrealistic, and if you think about it too hard, you'll realize it's a little weird to have a graph that does that. Don't worry about it. Just treat these as segment by segment, and don't worry about any discontinuities you might see at the sharp corners. And finally, final comment is we can answer distance questions always. We can see how far something went. Oh, how far? How far? That's a distance question. We can find out how far it went. We can only get the displacement if we have been given velocity, right? Because that's the thing, that's the vector quantity that we can use. One last question. I'm going to skip all the way down to the bottom. For the total trip, you can determine the displacement and the distance. Displacement's the easy one for the total trip because I see I started at 0 and I ended at 0. But distance for the total trip, I have to do a little work. It looks like during segment A, I got distance of 3. Oh, did I do this right? How far did the object travel? Oh, I'm messing up. Ignore what I just said. You can do distance and displacement. If you do displacement first, after that you can look at magnitudes and find out total distance. Ignore what I just said about 3 there. Okay, let's move on. You can determine for yourself whether you think the answer makes sense that we're getting and why it's true that the area represents displacement. You can check out this, pause the video, check out the slide if you find it interesting. But I really want to get into one little bit of what I call advanced material. So I made a claim earlier, this is really interesting. I made a claim earlier that for any curve, for any velocity time curve, the area under the curve is the displacement. It sounds so powerful, and it sounds so simple, and it is actually. It's simple and powerful. Let's figure out why that is the case. What I'm going to do to convince you is I'm going to take a curve here. Here's a velocity time graph, and I'm going to approximate it as a group of rectangles. So you can see I have, what, I don't know, about 20 plus rectangles here in the picture. And if you look at the number of, at any one rectangle, if you zoom in, like this rectangle here is pretty good to describe the area under that portion of the curve. And even this rectangle is pretty good to describe the area under that portion of the curve. You can see I sort of over-counted here, but I under-counted here, and they roughly cancel. So that's a pretty good approximation. Oh, but now I have a series of rectangles, right? So I can treat this graph as the sum of a bunch of rectangles. And any one rectangle, we've already convinced ourselves, is correctly giving the displacement, because it's a velocity time graph, area under the curve. And now we can see that if you have a curvy curve and you approximate it as a series of rectangles, you'll get the correct answer. If I wanted to be super perfect, like really precise, I would choose lots and lots and lots of these rectangles. I would make them smaller and smaller so that I would have less and less error, at the top. But that, folks, is calculus. If that felt good to you, you already had half of a calculus class, and you've learned the meaning of an integral. If you're studying calculus and you're studying integrals, you might be interested to know that a physicist named Isaac Newton was instrumental in developing calculus, and he did it because he needed the math to support his study of motion. So that's all I've got for today. Invite you to come next time and try more practice and whatever else we might bring. And for now, that's all I've got to say about area under the curve.